First, I'm going to explain how to use it, then why it works. I start by clarifying that the algorithm, in the form I present here, draws this line instead of that one. I chose this for reasons I summarize as aesthetics and convenience. One feature of drawing like this is that the lines are often symmetrical. First, having the coordinates ax, ay, bx, by of the line to draw, a is the first point and b the second, we need to set up a couple of variables to use in the loop. Sin x and sin y serve the same purpose as in Bresenham. They indicate which direction to move the pixel that will be painted. If you don't have a sine function, you can use this formula. If you're going to use conditions instead, you can omit the equality or place it on either side. You could even set that if ax equals bx, so sin x equals 1000, since if the equality is met, that coordinate won't be modified anyway. Size x and size y are used to later calculate height pixel x, height pixel y, and to indicate how many times the loop has to run. Keep in mind the line goes from the beginning of the first pixel to the end of the last, so the size is the difference between coordinates plus 1. Height pixel x and height pixel y are double the size in y and x respectively, in that order. Pos x and pos y are the coordinates to paint. They start from ax, ay. Dragged var is a variable to which height pixel x or height pixel y will be added, depending on the aspect ratio, to then compare and verify whether one coordinate needs to be changed. Once the variables are set, check if the line is more horizontal or vertical by comparing the sizes in x and y. Here, the equality must be included, but it doesn't matter on which side. Depending on whether it's more horizontal or vertical, dragged var is set with an initial value. Then the loop is executed. A multi-purpose loop that covers both cases can be made, but you need to add a second drag variable. So there's one for dragging in x and one for y, and the loop would have two conditional parts. It's more efficient to have two small loops than one big one. The loops for horizontal and vertical are the same, just with x and y swapped. They consist of two parts, an unconditional part and a conditional one. To verify whether a specific pixel belongs to the line without calculating the previous pixels, you need to compute some general things from the line, and then a small adjustment to the coordinates of the pixel to evaluate. These are calculations to establish the geometric context of the line in question. There's no need to calculate this context for every pixel, unless you are checking pixels for another line, in which case you do have to calculate the context for that line. Here too, things go times 2, because otherwise one of the terms ends up divided by 2 and causes floating point values. Height pixel x and height pixel y are double the size in y and x respectively, in that order. Then something to determine direction. It doesn't have to be plus or minus 1, just distinguish between positive and negative. And variables to remove the offset and invert coordinates, necessary so that lines of different sizes are equal regardless of where they are drawn. Min x, min y, max x, and max y. If the pixel coordinate to evaluate is test x, test y, then it must be transformed into test x, ax, test y, ax, which is its equivalent in the hypothetical geometric context. The conversion consists of removing the offset of the line and inverting coordinates if necessary. Whether to invert depends on the direction the line was drawn. Removing offset and inverting coordinates is needed so the rounding aligns. These are the directions. I'll write them as angles for clarity, but it's better to use aspect ratio and direction, dir x, dir y, to determine the case. With the coordinate conversion done, you can now do the check. The pixel, test x, test y, belongs to the line if the following conditions are met. The algorithm essentially consists of pretending that all lines are at 45 degrees and that all rectangles are squares, changing the scale of the axes. Also, note that for this algorithm, the only thing that matters when deciding which pixel to draw is the difference in a coordinate. It's not necessary to calculate the distance to the line. So, if I have this 17 by 7 pixel area, what I do is stretch it until it becomes a 119 by 119 square. 119 equals 17 times 7. The goal of this is to avoid floating point values from fractional slopes. Now the line that crosses this new area can only have a slope of 1 or -1. The pixels of this new area have been stretched. I call them hypothetical pixels. And now they measure 7 by 17 instead of 1 by 1. They measure the same as the original area rotated 90 degrees. In a square, the pixels that go corner to corner, slope equals -1, have the particularity that the sum of their x and y coordinates is constant. A pixel xy belongs to the line in a square if x plus y equals constant. This is for one of the two diagonals. For the other, a slight adjustment is needed, but the sum is also constant. The hypothetical area that results from stretching the original area is also a square, so this applies. Only now the pixels no longer measure 1 by 1. I call the width and height of these hypothetical pixels height pixel x and height pixel y. At this point, we have to shift into discrete geometry. While the total number of elements is size x times size y, the coordinate of the last element that still belongs to the area is size x times size y minus 1. Size x and size y are the dimensions of the original area. In this example, size x equals 17 and size y equals 7. I can determine which pixels belong to the line because if I take an arbitrary pixel and calculate its hypothetical version, the stretched version, the difference between the y-coordinate of the discrete element of the hypothetical line, the one from 0, 118 to 118, 0, and the y-coordinate of the hypothetical pixel must be positive and strictly less than the pixel's height. Now, I'll give an example of the full procedure to check if an arbitrarily chosen pixel should be drawn or not. First, I take the coordinates of the pixel to test and then its hypothetical counterpart. In this case, the pixel to test is 0, 6 and its hypothetical version is 0, 102. Second, I calculate the y-coordinate of the line in the hypothetical geometry, which I'll call y prime, the line that goes from 0, 118 to 118, 0. From that line, I know that x prime plus y prime equals size minus 1, and that size is size x times size y. From this, I can calculate y prime of the line from the x prime, because x prime is the same of the x-coordinate of the hypothetical pixel. Since it's a square, the distances on both axes are the same, but traditionally I solve for y from x. Then I calculate the difference. If it's positive and less than height pixel y, it means the pixel in question does belong to the line and should be drawn. Now I'll repeat the same procedure quickly for a few random pixels in column x equals 4. The constant I mentioned, this one, now becomes a value range, not a single number. So xy belongs to the line if the sum of x and y coordinates is greater than a minimum value and less than a maximum value. These minimum and maximum values correspond to the start of the hypothetical pixel being evaluated and the start of the next hypothetical pixel. The maximum value is a value that's never actually reached. It's size x times size y, the untouchable 119 of before. Therefore, the minimum value for the last pixel belonging to the area is maximum value minus one hypothetical pixel, which means it is size x times size y minus maximum between hypopixel x and hypopixel y. It is the maximum between hypixel x and hypixel y, because it defines how often the coordinate changes, which depends on the aspect ratio. If the original area is wider, the hypothetical pixels are taller, and the maximum is hypixel y. If it's taller, then the pixels are wider, and the maximum is hypixel x. That's the final raw formula. Just a small adjustment is needed, which I'll explain below. If you filter all pixels using this method, the result looks like a square, with the smallest side of the original rectangle. In this case, it's a 7 by 7. I'll overlay it to explain the next part. We could say that by changing y prime one by one, the y coordinate changes every hypixel y element. But since it's a square, we can also change x prime one by one, and y will also change every hypixel y element. So if I create a variable dragged var to accumulate the number of x prime elements, I can detect when the hypothetical pixel coordinate y changes, since I know that every hypixel y I'll be at a different y coordinate. This is for this example. If the line were wider than tall, the axes would have to be switched. That is, some y prime elements and change x every hypixel x. What I've explained so far is the essence of the concept. Now I'll explain a few more details, adjusting symmetry and why the algorithm doubles the size of the hypothetical pixels. First, symmetry must be adjusted. To do this, the calculation needs to be done at the center of the pixel, not at an edge. This is done by advancing the line by half a hypothetical pixel. But if the size of the hypothetical pixel isn't even, the midpoint falls between two discrete elements, which isn't possible. So, I force everything to be even by multiplying both hypixel x and hypixel y by 2, ensuring there's always a discrete element exactly at the center of any hypothetical pixel. Once everything is even, the line is offset by half a hypothetical pixel. This is why the algorithm starts with half hypixel x or half hypixel y, depending on the aspect ratio. That's what advances the line. That's why there are things like plus size or minus size, seemingly out of nowhere. It's actually half of a duplicated hypothetical pixel. Half of the double of something is the original something. In the equation that determines whether a pixel belongs to the line or not, the correction for the half pixel offset is made by also doubling the size of the hypothetical pixels. This was the previous maximum value. Now I double it, because the hypothetical pixels are twice as big, and subtract half a hypothetical pixel to advance the line. Remember that the hypothetical pixels are double the original size, so half of 1 is the original size. Here I subtract half a pixel because I'm shifting the environment instead of the line. I'll also mention that checking the aspect ratio to decide which of two loops to run is useful because if the rectangle is wider than tall, it means that in every iteration the painted coordinate moves in the x direction. So there's no need to calculate when to move in x because it always moves, only when to move in y, and vice versa when it's taller than wide. This allows two small, cheap loops instead of one large, expensive, multi-purpose one.